So hello, my name is Mikhail Lebedev, and I would like to present you our research of open source tools for neural network inference. So I'll start with a small introduction and background. So I think many of you know that the development of hardware is time and resource consuming process. So some people try to use synthesis to ease and accelerate this process. Synthesis is the process of transforming some high-level behavioral model into the low-level hardware model in, well, it's actually usually it's an RTL model, which can later be transformed into an ASIC or an FPGA bit stream. We can divide synthesis into three levels. The most highest level is obviously the high-level synthesis, then goes the so-called middle level synthesis, and the lowest level is hardware construction. So some words about these levels. Well, as I have said, the hardware construction level is the lowest. On this level, the input model represents the system and low-level architecture. There are many hardware details, and actually this level is usually very close to RTL development. On this level, such languages as Chisel and BlueSpec are usually used. So the next level is the middle level. Here, the input model usually represents the overall system architecture and maybe some hardware details, but low-level details are omitted usually. And the most abstract level is the high level. So there we can provide no architecture details or hardware details, only the algorithm, some abstract behavioral model written in usual languages like C++, Python, and others. And here there are many domain-specific languages, for example, to describe neural networks. So not only me, our team has conducted research on high-level synthesis this year. We have reviewed several hundreds articles, patents, and found over 50 open source tools. And only 12 of these tools were good enough for evaluation. So we have evaluated these tools using 4 tasks, 3 algorithms, and the part that I'm presenting, some neural network models. Our main question was if we could use open source tools for hardware synthesis. So let's start with the neural network part. First of all, I would like to say some words about the neural network formats which are used in different tools nowadays. The most popular formats are ONNX, TensorFlow, and Keras. So we have used these formats in our evaluation part. The other formats are not so usual. Well, so on this, in this table, you can see the tools that we have reviewed. These tools are very different. They are developed by big and small companies, universities, and even some people. We can divide these tools into three groups. The first group consists of the tools which run inference of neural networks on the fixed architectures like CPUs, GPUs, and tensor processors, and others. The second group are the tools that use specialized coprocessor cores to run neural networks, and these cores can be programmed into the FPGA or maybe some hardware. And the last group consists of the tools that can synthesize RTL directly, or using some conventional high-level synthesis tools like LegUp or Vivado. So our goal here was to implement our neural network models on the FPGAs. So that's why we have chosen the tools from the second and the third group. So here you can see our evaluation models. These very small models of the neural networks. This is because we don't have big FPGAs. We used the small ones. I'll talk about this later. So the first two models are the neural networks, which can recognize the digits from the MNIST dataset. The first network is fully connected, and the second network is a convolutional neural network. And the last group of models, these models are synthetic matrix multiplication, which we used to evaluate the LeFlow tool. So here you can see our environment. We've had 3 development boards, 2 based on Intel Cyclone 5 system on a chip, and 1 based on Xilinx Zinc 7000 system on a chip. We have also run inference on the Intel Core i7 CPU and NVIDIA GPU. Here I should note that we have used the default settings of the tools, so we have not adjusted these tools to our models. So next we have, I'll say some words about the results. Only 2 open source tools have managed to run our examples on FPGAs. The first one is TVM tool plus versatile tensor accelerator coprocessor core, and the second tool is LeFlow tool. But it hasn't managed to synthesize the convolutional neural network. The other tools have failed but because of different reasons, like errors, licensing problems, or some closed implementations. So I would like to talk more about the tools that succeeded. The first one is LeFlow. This tool has been developed in the University of British Columbia. It is not only the tool, but also a root of synthesis. So here you can see the input TensorFlow model is compiled by the XLA compiler, which is a part of the TensorFlow framework. Then the LLVM model of the input neural network is transformed by the LeFlow tool, which transforms it into a more hardware-style model. It adds some additional variables, signals, and then this transformed model is synthesized by the GAP synthesis tool into the Verilog model. So here you can see the resource usage of the synthesized designs, the models, and also the RTL code size and the maximum frequency of the synthesized designs. On the next slide, there is the performance results. Here you can see that the simplest model achieved acceleration, but the other models were significantly slower on FPGA than on CPU. We have calculated the FPGA time using the simulation time and the maximum frequency of the designs. The next tool is the TVM tool, which has been developed in the University of Washington, and it's now supported by Apache Foundation. So as input to this tool, we use the ONNX representation of our models. It's translated into the computational graph, LLVM operations, and the weights. This model is then transferred onto the system on a chip, where the runtime environment is running on CPU, and the VTA accelerator is running on the FPGA. So the runtime takes the representation of the model and feeds it into the accelerator and gets the results. So here you can see the VTA accelerator structure. It consists of the instruction fetch module, which fetches instructions from the memory, the load module, which loads the input data and the weights, and transfers them to the compute module, which performs tensor operations and matrix multiplications. And later, the store module stores the results into the memory. So here you can see the resource usage of the VTA core. Well, it's the same for all models. It's a universal core, so it's the same for all the models. And this slide presents the performance results. We have run the original Keras model on the standard Keras runtime on CPU. Then we have run it then we have optimized and run it using the TVM tool, and on CPU and on GPU. So here we can see that the simplest MNIST-FC model has been accelerated on the VTA core, comparing to the original Keras runtime, but in all other cases, the VTA core was significantly slower than the other platforms. So we tried to optimize and quantize the convolutional model, but we haven't achieved significant acceleration for it. So some conclusion. So we can see that inference on FPGAs is possible using the open source tools, and we can even accelerate simple neural networks, but these tools are useful only for some low power applications which do not need good performance. If we need performance, we need maybe bigger FPGAs with bigger specialized cores. But the best results, but GPUs are still the fastest platform. So thank you. Questions?